Hello all, in today's tutorial we are going to discuss how to use Xilinx IP core within your Verilog code. So in our previous project we have used IP cores from Xilinx, we have used the DMA controller, we have used the Axie interconnect, we have used the Zinc PS processing system. These are all IP cores from Xilinx, but we use them in the IP integrator flow or the block-based design. But today we are going to discuss how to use Xilinx IP cores within your Verilog code. Now, why you want to use Xilinx IP cores within your design again depends upon the requirement. Sometimes these IP cores you cannot be inferred through your coding, like IP cores like the PLL or MMCM, which are used for changing the clock frequency. That code you cannot directly write in Verilog. That is one reason. Sometimes you want to use Xilinx IP cores because they are more optimized. So even if you write the equivalent Verilog code or VHDL code, if you directly use the IP cores from Xilinx, most probably they will be giving better performance in terms of clock as well as resource utilization, because these codes are written by Xilinx engineers, so they are more optimized. So we are going to quickly see how to include these codes in your code. I will introduce few of the IP codes, but a large number of IP codes are available from Xilinx. Either they are totally free, and some of them you get license for only implementation, but you cannot run it on hardware. You can just go till implementation, you can simulate it, but you won't be able to generate bitstream. For generating bitstream, maybe you have to take additional licensing by paying. So different kinds of models are available, but of course all simple IP cores are available for free. So first I am going to show you a FIFO. So FIFOs are very commonly used IP cores within your Verilog code. So we usually use FIFOs when your application cannot be completely stream based. In the previous image processing application, I have shown how can you do a streaming. That means your IP cores, it doesn't have to store your data internally. It can process data as soon as the data comes. But in many cases, that is not the case. Your IP or your logic may not be processed the data at line rate. It will have to store initially data somewhere, then it will have to process data later. So in that case, you have to temporarily store data somewhere, and in that case FIFOs are very useful. Now, as I said before, writing a FIFO in Verilog, it is not that challenging, but using Xilinx IP core for FIFO, and they give different flavors of FIFO, so we will see it. So I'm starting a new project, and let me call it IP evaluation, because I'm going to use the same project for testing different IPs, and all remaining settings remain the same. You should go to this IP catalog option. We are not going to this block design this time. We are directly writing our code in Verilog. So IP catalog and search for FIFO. And as I mentioned before, you will get different flavors of FIFOs. You can have FIFOs with Axie for stream interface, and FIFOs with so-called the native interface, the traditional write enable, read enable interface. So different kind of FIFO. So let's use this one, FIFO generator. So you just double click it, and it will open a wizard, and where you can specify all your options. So as you can see, the first one is the name of the FIFO, the module name. So let's call it my FIFO. And here you can see different interfaces, what kind of interface you want to the FIFO. And on the left you can see a block representation also. So the native interface, that is a traditional FIFO interface, the simplest one. You have write enable data in and full here, and read enable data out and empty here, and of course there is clock and reset signals. So in this interface, if you want to store some data to the FIFO, you will make the write enable signal high, along with you will place the valid data on the in interface. If the FIFO is full, that means if it cannot store any more data, this signal will become high. So if you want to read from FIFO, same way, you will make the read enable signal high, and in the subsequent clock, the first data in the FIFO will come out through this interface. So there is no concept of address in FIFO because it's a first in first out kind of memory. So there is no special need for address from your side. That's all managed inside the IP cores itself. So if you want to write, make this signal high, give the data here. If you want to read, make this signal high, and the valid data will come out through this interface in the next clock. Now, if there is no data in the FIFO, this signal will go high, the empty signal. So this is the traditional FIFO interface. Now, if you choose axis stream interface, you will see the interface is changing to the axis stream standard, axis4 stream standard. We have the slave interface on the left, which is used for writing to the FIFO. So if you want to write, you will place the data here, you will make the valid signal high. And if there is space in FIFO, so this ready signal will become high from the IP cores. That means your data got stored. If ready signal is low, that means FIFO is not ready to write your data, which basically indicates the FIFO is full, so your data won't get stored. Okay, so if you want to read from FIFO, that comes through the master interface. So what you should do is you should make this signal high. M-axis ready signal high. That means you are ready to accept data, and if there is data in the FIFO, this T-valid signal will become high and you will get the data through this interface. And again, you have clock and reset signal here and some additional busy signals here. Now there is memory mapped FIFO also. So in this case, it's not really a FIFO because you have to provide the address details also. So this is the interface for writing, this is the interface for reading. So you can say it's quite complicated because it's a axis4 memory mapped full interface. So traditionally or usually we always go for either this native interface, which is the simple one, or the axis stream interface, which is also quite simple. Okay. Now another setting that you can set is this one. If you are going for axis stream, that option is going away. But if I choose native, there is an option here how this FIFO should be implemented inside FPGA. Now I hope from my first lecture you remember inside FPGAs we have lookup tables and LUTs. In addition to that, the new Xilinx FPGA, they have other primitives also, and one of the most important primitive is something called a block RAM. So they are small blocks of memory, small built-in memory inside the FPGA. For the Zinc FPGA, which comes under 7 series FPGA from Xilinx, the size of this small memory is only 36 kilobit. Okay, one small memory is only 36 kilobit, and depending upon the FPGA, the number of these small memories varies, like the lookup tables and flip-flops. So you cannot build very large memory, but if it is few kilobytes, you can build such memory inside FPGA using these small memories also. So if you choose block RAM option here, the implementation tool is going to use these small memories to implement your FIFO. And if you choose distributed RAM, he is going to use the lookup tables and flip-flops to implement your FIFO. So the difference between BRAM and distributed RAM, if you are going with the distributed RAM, he is going to, as I mentioned before, lookup tables and flip-flop. So he will take a lot of LUTs and flip-flops inside the FPGA. So there will not be enough resources for other components that you want to implement. And also the maximum clock frequency supported by block RAM based implementation will be more than the maximum clock frequency supported by the distributed RAM. Okay, so there are differences there. And again, based on what option you choose here, what features you can use also varies. That is the table showing here. Okay, so let me try to explain few of those features. One feature is called common clock or distributed clock. Again, this is one area where we will use a lot of FIFOs. For example, you are getting data at a very high rate, say 200 megahertz. That's the clock frequency at which the data is coming from external world or some other logic. But your logic, it cannot process data at 200 megahertz because of the critical path in your circuit. Your circuit can process data, say, only at 150 megahertz. So there is a clock mismatch. Data is coming at 200, but you cannot process it at 200. You can process it only at 150. So what you should do, first you have to store the data somewhere, usually in a FIFO at 200 megahertz. Then you need to read from FIFO and process it, say 150 megahertz. Okay, so you are right, clock frequency and read clock frequency are different. So these kind of FIFOs, we call them asynchronous FIFOs because the clock frequencies are different. That is one feature we usually use. Another common feature that we use is something called asymmetric implementation. We call them assymmetric FIFOs. Here, what it means is the data width of the write port and the data width of the read port are different. For example, you may be writing data at 8 bits wide. Your write data is 8-bit, but while processing, you want to process at 32-bit. So that is possible. Okay, so your write interface, this D in interface, this will be 8-bit, and this interface could be 32-bit. That means you'll write 32-bit data using 4 clocks here, but when you read from here, you will get that entire 32-bit in one shot in a single clock frequency. So those FIFOs, we call them as asymmetric FIFOs. Other features you can read in the documentation. So if you go here, click here, the documentation will come for the IP core, so you can read the details here. So a lot of features are supported depending upon what kind of implementation we choose. So this time I'm choosing common clock block RAM. That means the read clock and the write clock, they are the same frequency, and it will be implemented using block RAM. If you want different read and write, you should choose independent clock block RAM. Okay, fine. So next one is some other options. So here you can choose what is the width of the write interface and what is the width of the read interface. Okay, so let's write data at 8-bit and how many data you want to store in the FIFO, basically the depth of the FIFO. Okay, let's keep it at 1024. Here you choose the read width. Okay, so see here you have the option like 1, 2, 4, 8, 16, 32, 64. So your write width and read width can be different, which makes it asymmetric. So read width also, let me keep 8 for the time being. So if it is 8, from read port perspective also the depth is 1024. If you make it 16, you are reading 16-bit in one shot. So from read side perspective, the depth of the FIFO is only 512, because if you multiply these two numbers, you will get the same result as this, which is the total capacity of the FIFO in bits. Okay, so here let's keep it 8 itself. Choose standard FIFO. What is first word fall through? Maybe we'll discuss later. Reset type, synchronous, asynchronous. That is this reset. If you uncheck it, your FIFO, it doesn't have any reset. Okay, again, if you want to reset a FIFO or not, up to you. If you reset the FIFO, all the data in the FIFO will be flushed. Okay, so that's what is happening. If you want that property, you can set the reset, and if you never want to reset a FIFO, okay, you of course uncheck it. Now it is also saying read latency 1. That means you place your read enable, the data out will come only in the subsequent clock edge. Okay, so that is what is making it 1 clock latency. Now if you check this option, output registers, what is going to happen is he will put additional register at the output data. Okay, so that will make your read latency 2. So if you place a read enable, the actual data will come not on the next clock edge, only after one more clock edge. So it will take 2 clock cycles after you place the read enable signal for the data to come out. Okay, but the advantage is if you add this option, it is effectively adding a kind of pipelining which will improve your maximum clock frequency. Now he's asking where that additional registers should come from. They can come from so-called embedded registers or fabric registers, embedded and fabric. Again, details you can read in the data sheet. These are low-level details. Maybe this time we don't want this additional pipeline, so you can keep it unchecked. Now status flag. So these two are two status flag, full and empty. They are basically saying whether FIFO is full, and this is saying whether FIFO is empty. In addition to that, you can have other status flags also. For example, almost full. When I check it, you will see that that signal is also coming. So almost full, almost empty. So again, the exact numbers I don't remember. I guess almost full flag will become high. Yeah, the FIFO has one more position to fill. Okay, so this, so you will in advance you will know the FIFO is going to get filled up. And similarly, almost empty, if you check it, you will see that signal is coming. So this flag will go high when there is only one more data in the FIFO. So if you read that data also, it will become totally empty. So these are the status. Now you can have something called programmable full and programmable empty. So if you set that option, instead of you can use the full and empty, of course, then there is this additional programmable full here. So this signal will become high when the FIFO has as many data as you specify here. Okay, so if I specify 256 here, that means when the FIFO has 256 data, this signal will go high. Same way you can set programmable empty also. So that when only that many data is left inside the FIFO, that empty flag, programmable empty flag, will become high. Okay, so these are all additional features available. Again, depending upon the application, we may use it, we may not use it. Now data counter, by default there are no data counter. If you enable it, this interface will basically tell you how much data are there in the FIFO. Okay, so the maximum capacity of FIFO, we set it as 1024. So that's why it is coming as 10-bit wide. Okay, if I increase that size, the width here also will increase. So this interface will basically tell you how many data are currently available in the FIFO. Again, if your application needs this information, you can enable it. Otherwise, you can keep it unchecked. Now this is the overall summary. So here you can see like we chose block RAM for FIFO implementation. So he's basically saying how many block RAMs he's going to use. So I mentioned each block RAM is 36 kilobit, but Xilinx has a feature they can divide this 36 kilobit RAM into two 18 kilobits RAM. So he's saying with current setting, your FIFO will take only one 18 kilobit RAM. Now if you go and increase this, the FIFO size to some large value, and if you come to resources summary, you will see like it has gone up. Yeah, so if I set the depth as 16K, so the total capacity, this is 1 byte, so it is 16 kilobytes is the total capacity of RAM. He's saying he will need 436 kilobit RAM to implement your 16 kilobyte RAM. Okay, so yeah, so that depends upon the settings that you choose here. And read latency is 1, and all the details that we set. So once you have done all this, you click OK, and he will create a folder called IP within your project itself, where he's going to store the details about your IP. Now when this screen comes, you can choose generate. Okay, what it is actually doing, let me explain. Now Xilinx, they are not going to give you the actual Verilog code for the FIFO. What they will provide you is a netlist. So currently Vivado is synthesizing that FIFO in the background, and he will make a netlist which you will be able to use in your design. Now the netlist that Xilinx generates, they are called DCP file. Okay, they will have the extension .dcp, which stands for design checkpoint. This is a proprietary netlist, not like the netlist that we have seen last semester, or EDIF netlist, or even Verilog based netlist. This is a proprietary netlist. Only Vivado can understand the content of that netlist. So if you go to IP sources here, yeah, here is your FIFO. So whatever IP you are using in your project, it will come under sources, under IP sources. And if you expand this, you will see my FIFO.dcp. It's in red. That means he hasn't finished generating the netlist yet. He is running it in the background. So once he finishes it, this file will come here. So this is the actual netlist .dcp file, .design checkpoint file. Now if you go to hierarchy, yeah, you will notice it is not a Verilog file. Okay, so this is called an XCI file, .xci file, Xilinx core integrator, I guess. That is the IP file. So in future, if you want to change any property of your FIFO, what you should do is you just double click this file. The same wizard will come up, so you can change whatever property you want and say OK again. So he will again synthesize the netlist. You change any property here, he will resynthesize your IP code, because effectively this is going to some Verilog source code. So any change in the source code you have to resynthesize. Fine. Next question: how are you going to use this FIFO within your design? So as I mentioned before, Xilinx, they are not going to give you the complete Verilog source code, but the only information that you want to use an IP within your code is like what is the name of the IP and what is the interfaces to the IP. That's the only information that you need. Okay, that they will provide. So if you come back to this IP, if you expand this, you'll see this option, Instantiation Template. Okay, so if you expand that folder, you will see two files, myfifo.vho, myfifo.veo. The VHO file, this is an instantiation template in VHDL. This VEO is an instantiation template in Verilog. So if you come down, you will see the instantiation template. Okay, and this we have seen before. This is how we instantiate modules within other modules. So he's saying like the name of the module is myFIFO. The instance name you can give whatever you want, and these are the ports to the FIFO, and whether they are input or output and what their widths are, they are giving as comments. Okay, so this is the only information you need if you want to use this IP within your design. Okay, now he has finished synthesize, so you can see now the DCP file is here. This is the netlist file. You cannot directly open and view it at this point, so yeah, so it's pretty useless for you. But as far as Vivado is concerned, he will use the netlist when he goes for the implementation step. Okay, so he will combine this netlist with the netlist of the remainder of the circuit, and he will make a single netlist and he will implement it. That's what is going to happen. So let's do one thing. Let's use this FIFO within your design. Okay, so you will copy this instantiation template and you will use it within your Verilog source code. So let me make a Verilog source code now. Let me just call it FIFO test.v. Okay, so I have it here, and I want to use this FIFO in my design. So I just copy paste that instantiation template and give the instance name my FIFO. Let me call it my FIFO itself. Now if you have other part of your design, of course you can write that and integrate it with this FIFO, but currently I don't have any other design, any other code. So I will just keep this code itself and directly interface it with the top of my module. Okay, so let me call it, I have input clock, I have input reset, I have input 8-bit data, so 7 down to 0, in data input, let me say in data valid, let me say output 7 down to 0, out data, and let me say input read data. This is my interface from the top. So how can I connect it? This clock I can directly connect here. This reset I can connect here. So now the FIFO is not axis based FIFO, so the reset is active high, not active low. Okay, so if you want to reset FIFO, make the signal high. Data in, I can directly connect the in. Write enable, I can directly connect data valid, because when data is valid, the signal will become high. Okay, so that is effectively connected to write enable, so this data will get stored in the FIFO. Now read enable, okay, read data I can directly connect here, layout I can connect here. Now full and empty, again, depends. If your logic wants to check whether the FIFO is full before writing to it, you can add that. The only thing is, if FIFO is full and if you try to write to that FIFO, that data won't get stored there. That's all. Same way empty, if the FIFO is empty and if you try to read from FIFO, some data will come out, but it will not be a valid data. That's it. So I am not connecting them. I just want to test my FIFO. So now once you save it, you will see in the hierarchy, this IP goes under FIFO.test. So this is instantiated within this. Now we can simulate and see how the FIFO is running. So you can go ahead and choose run simulation, run behavioral simulation. Now if you are using Xilinx IP cores, even for behavioral simulation, you need to give some respect for the clock signal. So don't try to run it at 1000 megahertz or things like that. Okay, so we usually say in behavioral simulation, it doesn't matter what the clock frequency is, you can put as much as you want. But once you have IP cores, give some respect. So maybe run it 100 or 200 or 250 megahertz, not more than that. Again, depends on the FIFO, depends on the IP, because there are restrictions on what's the maximum clock frequency the IPs are running. So internally, I guess the simulation model is looking at that frequency. So if the frequency is too high, most probably your IP might not run. So most of our Z design, it is running at 100 megahertz. So here also, let me run it at 100 megahertz. So this is my clock. So reset initially, let me keep everything in reset. In data, let me make it 0. In data valid, let me make it 0. Read data, let me make it 0. So all inputs are forced to 0. And let's run for 2 clocks. Okay, now let me remove the reset. Now let me write some data to the FIFO. Okay, so let's make it rising edge. So let me run for 5 nanoseconds more. Okay, so this is where I'm going to place my first data. So in data, let me write 100 unsigned decimal, and sorry, false constant 100 unsigned decimal, and data valid is 1. Okay, so I made it after this clock edge effectively, so it might be getting written here. Okay, so let me write some more data. So I'm writing 100. Let me write 123 unsigned decimal. Okay, false constant. Let's write unsigned decimal 225. Okay, let me write 3 data. So in this clock, on this clock, the 255 might be getting stored. I don't have any more data, so let me make in data valid 0. Okay, so remember this signal is getting connected to write enable of the FIFO, and this is connected to the data in. Okay, so they might be getting stored there. Now let me try to read from the FIFO. So for that I need to make this signal high. So force constant read, I made it high, and you can see the first data came out inside decimal. So I made the read enable high after this clock edge, and the data is coming only on the next clock edge. Okay, so this makes one clock latency for reading. Now if you keep on making the read signal high, so it will keep on giving you data now. Okay, so one interesting thing is maybe we'll see how signals are coming out of FIFO also. So let me make a divider here, and FIFO, you can add the FIFO signals also here. Yeah, so as I said before, this in data valid is connected to write enable, so you can see they are the same, and D in and in data they are the same, read enable and this read data they are the same, and D out and out data they are the same. Okay, so let me run once more, and you will see as soon as, okay, I can't see the previous signal here, but if I restart simulation you will be seeing the empty signal, it becomes high as soon as this last data comes out. Now FIFO is empty and your read enable, you are keeping it asserted, but this data will not change because the FIFO is empty, the last data is already here. Okay, so let me show it to you once again. Read data force constant to 0. Okay, so let me write one more data. Now you'll see the empty signal is high here. So in data force constant, let's write 300. In data force constant and decimal. Oh, because we have only 8-bit. Okay, so this is the maximum value. So let's write 3 to 30. And in data valid constant 1. And run for 1 clock. Okay, look at the empty signal. What will happen to that? So on this clock, it might be getting stored. So I'm making it 0 here because I have only one data to write. So let's see on that clock edge, slightly after that clock edge, the empty signal became high because the FIFO is no more empty. You have one data in the FIFO. Okay, now maybe one more interesting thing, this is what I was trying to mention. Although this is behavioral simulation, the Xilinx IP, they have some timing information. So you'll see the empty is not becoming low at the clock edge. It is happening slightly after the clock edge because practically this is how it happens, right? So there will be some clock to output delay. So empty is becoming low only after the clock edge, even in functional simulation. So it is supposed to change on the clock edge. They are using some timing information here also. Anyway, now let me try to read data force constant 1. Okay, so data might be coming on the next clock. I wanted to read only one data, so I'm making it high and I'm making it low. The data came out here 230, and along with that data, empty also became high, saying like the FIFO is empty. Now if you want to see the full signal going high, you will have to write 1024 data because that's the capacity of the FIFO. So if you write 1024 data like this, or I can just try it, I can make in data valid 1 and run for 1025 nanosecond in one shot. Same data is getting returned to everywhere. you will see, yeah, 1024 data gets stored, the full signal became high. That means the FIFO is full. Whatever data is you are subsequently writing will not get stored in the FIFO. Fine. So I may try to show you a symmetric FIFO also, and try to simulate that. So let me go back to Project Manager, double click on my FIFO, and let me change the port width. So here I am writing at 8, and let me try to read at 32, and let's see what happens. Okay. So remember to do this generate before you run the simulation. Otherwise also, if you click generate simulate, first he will run this generation and then only the simulation will run. So he will generate this new .tcp file, and you will see like my FIFO underscore sim underscore netlist.v. Okay, so he will generate a Verilog model for your FIFO. This is not a real synthesizable code. This is a model for your FIFO, which is used only for simulation purpose. Because of course for simulation you need some Verilog source code. So he is going to use this one. But this can be used only for simulation. For implementation, he will directly use this netlist file. Okay, so now the synthesis of IP is completed. So if you go to Instantiation Template here, reload, and you will see now D out. He's saying it's 32-bit wide, okay, because we have changed the bit. Now in the Instantiation Template, there is no change. There is change in command, but of course the actual template hasn't changed because the name of the port is still D out. So the only difference that we need to make is in our source code, this out data should be now 31-bit, right? Because now this is 31-bit, so out data should be also 31-bit. Okay, save it and go back to run simulation. And since you changed the source code, you need to relaunch simulation. Click this button to relaunch. And you can see here also he automatically changed it. Okay, so restart. Force clock and 01 10 nanosecond. Let's reset. Okay. So you'll see like he's already saying it is empty at the beginning because there is no data in the FIFO. So let me reset reset. Okay, now let me run 10 nanosecond each time. Okay, let's go to the first image. Okay, let me write the first data. So in that force constant, let's write in hex so that things will be clear now. F5. Okay, in data valid force constant 1. Okay, so I wrote F5 here. Next, I'm writing force constant F1. Okay. Now you will notice previously, as soon as you write the first data, your empty used to get deasserted, saying like the FIFO has some data, but not now. Okay, why? Because now your read width is 32. That means for making one read, you need at least 4 write operation. Okay, because 4 write operation will constitute 4 bytes. And as far as the read port is concerned, one read is 4 bytes, 32-bit. Okay, so unless there is 32-bit data inside the FIFO, he cannot read. That's why the empty is still showing high. He's still empty. You cannot still read because not enough data. Force constant, let me call it 12. Okay, and force constant, okay, for E. Okay, let me write one more. Force constant FF. Okay, I'm done with writing. So valid signal, force constant 0. Now if you come here, as soon as I write the fourth one, the empty signal became low, saying like he has some data. Now let's see what data comes out when I am reading. So 1. Okay, made the signal high here. Let me keep it high for one more. Okay. You will see this is the D out. Here also you can see this is the D out. Let's make it in hex. So the data is F5, F1, 1, 2, 4E, which is these 4 bytes combined. Okay, so your write width is 8, but when you read, you got 4 bytes in one shot. So this makes it a symmetric FIFO. Now this FF will not come out until you write 3 more bytes. Okay, only once he gets 4 bytes, he can make one read. So this data came out. Along with that, you will see the empty signal also came out. Basically, he's saying like you have no more 30-bit, 32-bit data in the FIFO. So I hope you understood it. So more IPs we might be using as we go along. So the most frequently used ones are FIFOs, as I mentioned. Another one that we frequently use are RAMs, the memory itself. Okay, so you may have to build small memory inside your IP, especially if you are doing image processing, video processing applications like that. Maybe you want to initially buffer some image data before processing it. So the difference between FIFO and our traditional memory is in FIFO, if you store some data, you can read it only once. Once you read it from the FIFO, it is out of FIFO. But there are scenarios where you want to store data for quite a long time and you want to read multiple times from the memory. For example, if you are sorting numbers, you may have to read the same number many times from the memory. In that case, FIFO may not be appropriate, because you can read only once from FIFO. In that case, instead of FIFO, you will have to implement a small RAM. So if you go here and search for RAM, you will see like RAM and ROM, and you can choose either distributed memory generator, means he is going to make RAM using LUTs and flip-flop, or block memory generator. He is going to make the RAM using the built-in block RAM. Another frequently used one are these PLL. So we have to search for clocking wizard. So this IP is used for the clock frequency. So remember when we did the SPI controller, my input clock frequency was 100. Then using some logic, I converted into 10 megahertz. But that is not a right way of doing it. Clock is a special signal. You should not use a logic to convert it into higher frequency or lower frequency. So we have to use some built-in circuits inside the FPGA to do it. And usually Xilinx FPGA, they have 2 built-in small components to do this clock conversion. One is called a PLL, phase lock loop. Other one is called a MMCM, mixed mode clock manager. So if you want to use them, of course you cannot infer them through your Verilog code. You should call this IP wizard and instantiate them. So for example, here you can see the clock wizard, and I can say like my input clock frequency is 100 megahertz, and you can choose what is your desired output clock frequency. I can say my desired output clock frequency is 10 megahertz. So he takes a 100 megahertz clock and gives you 10 megahertz output, right? So 100 megahertz goes like this, 10 megahertz comes like that. The interesting thing is one such IP can give you up to 7 independent clocks. So here I need a 10 megahertz. I also need a 20 megahertz here, you can do it. I need 50 megahertz, that will come through here. So that's the beauty of this. Okay, so he can give you up to 7 different clock frequencies from a single input clock frequency source. Now, how a PLL works internally, again, those who are interested, you can go and check how PLLs work, phase lock loop. But to use it, it's really straightforward. You can use this IP. So again, PLLs or this clock wizard is a widely used IP course. Okay, so I hope in some of the future tutorials we will be using more IP cores from Xilinx within your code. So details we will discuss at that point in time. Okay, thank you.